So this lesson is on partial derivatives. Let's look at an example. So we have f of xy is 4x cubed y squared plus 2xy to the fourth minus 3x plus 2y plus 9. If I want the partial derivative of f with respect to x, sometimes written as f sub x, we take the partial derivative with respect to x of each piece. The derivative of the sum is the sum of the derivatives. We know that from calculus. So looking at this, we take the derivative of each piece, but now it's the derivative with respect to x. So x is thought of as the variable, and y's are perceived as constants. So the y's can all come out in front of the derivative operator, as can the constants. So let me stick with this notation this time. So 4y squared comes in front. 4y squared times the partial with respect to x of x cubed. Plus here, the 2y to the fourth comes out in front, times the partial with respect to x of x. Now here, if you only have a function of x and it's a partial with respect to x, then you just take the regular derivative. So the derivative with respect to x of 3x is 3. No issues there. Plus the partial with respect to x of 2y. Well, y is thought of as a constant here since we're taking the partial with respect to x, and the derivative of a constant is 0, as is the partial with respect to x of 9 going to be 0. So now we have just functions of x after our partial derivative operators. So once that's the case, you just take it as a derivative. So what does that give me? We get 4y squared times 3x squared plus 2y to the fourth times 1 minus 3, which gives me f sub x, my partial derivative, will be 12 x squared y squared plus 2y to the fourth minus 3. That is my partial derivative with respect to x for that function. Now let's go ahead and do a partial with respect to y. So there's our function. We want to take the partial with respect to y of that function. So we take the partial with respect to y of each piece. Again, the derivative of the sum is the sum of the derivatives. So again, derivative of the first piece plus the second plus the third plus the fourth plus the fifth. So what does that give me? What is my f sub y going to be? So now y is thought of as the variable. X's are perceived as constants. So the constants can come out in front of the derivative operator. 4x cubed can move in front. 2x can move in front because those are perceived as constants. We are fixing x in this discussion. So we get 4x cubed times the partial with respect to y of y squared plus 2x times the partial with respect to y of y to the fourth minus. Well, here we go. The partial with respect to y of 3x. 3x is perceived as a constant, and the derivative of a constant is 0. Here, the partial with respect to y of a function of y, you just take the regular derivative and get 2. The partial with respect to y of 9, that is a constant again. That is going to give me 0. So then what does f sub y become? 4x cubed times 2y plus 2x times 4y cubed plus 2, which gives me my partial derivative of f with respect to y, 8 x cubed y plus 8x y to the third plus 2. So next up, we've got g of xy is 6 divided by xy squared. So I want to get g sub x, the partial derivative of g with respect to x. Also, the partial of g with respect to x, which is the partial with respect to x to 6 over xy squared. So how do you think this is going to work? Remember, we can pull constants out in front. What is perceived as a constant here? Well, 6 is perceived as a constant. Y squared is perceived as a constant. So we can pull out 6 over y squared times the partial with respect to x of 1 over x. So what do we get there? G sub x is 6 over y squared times the partial with respect to x 1 over x is the same as x to the negative 1 power, which will give me 6 over y squared times negative 1 x to the negative 2, which finishes me at negative 6 over x squared y squared for my g sub x, my partial derivative of g with respect to x. Now, how about the partial derivative of g with respect to y? G sub y, the partial with respect to y of g, which is the same as partial g partial y, just getting used to the notation, is the partial with respect to y of 6 over xy squared. Now, x is perceived as a constant, so I can pull the 6 over x out in front. So we have 6 over x times the partial with respect to y of what's left here, 1 over y squared, which is 6 over x times the partial with respect to y of y to the negative 2, which is 6 over x times negative 2 y to the negative 3, which will give me negative 12 over xy cubed. Okay, this time I want to look at f of xy is the sine of xy squared. So f sub x, which is the partial with respect to x, sine xy squared. How am I going to do this? Well, we have to think of the chain rule. So the partial with respect to x of the sine of something is the cosine of that something times the partial with respect to x of that something. So what we get then is we get f sub x is the cosine of xy squared. Now we can pull the constant out in front. X is perceived as the variable, so y squared is perceived as my constant. So I'm going to pull that y squared in front of my partial derivative operator. So it's going to be times y squared times the partial with respect to x of x. So what is that going to give me? Cosine xy squared times y squared times 1. And normally, how would we write that? We would write that as y squared cos xy squared. That's my partial with respect to x. Now, how about the partial with respect to y? What will that be? The partial with respect to y of the sine of xy squared. Again, same chain rule. The derivative of the sine of something is cosine of the something times the derivative, in this case, partial derivative of the something. So this time y is perceived as the variable, so the x is perceived as a constant, and the x can go in front of the partial derivative operator. So that we get f sub y is cosine of xy squared times, pulling the x out, times the partial with respect to y of y squared, which of course is just 2y. So where does that leave us? F sub y is cosine xy squared times x times 2y. And how normally would we write that? F sub y is 2xy times the cosine of xy squared. And let's finish with one more problem. We highlighted the chain rule in the last problem. So let's highlight the product rule here. And remember that uv prime is u prime v plus uv prime. So I'm going to define u and I'm going to define v here to get my partial with respect to x. So my goal is to find the partial of g with respect to x, also notated as g sub x. So I'm going to define a u and a v. U is x squared, v is the tangent of xy squared. what I typically call u prime, this time is the partial with respect to x, since we're taking with respect to x here. The partial with respect to x of x squared. And v prime will be the partial with respect to x of the tangent of xy squared. Okay. The partial with respect to x of x squared is just 2x. That's not a problem. V prime, the partial with respect to x of the tangent of something is secant squared of the something times the derivative, in this case, partial derivative of that something. So what do we get for v prime? Secant squared xy squared times, now x is perceived as the constant, excuse me, as the variable. Y squared is perceived as a constant. That comes in front of the derivative operator. So we get y squared times the partial with respect to x of x. And we get v prime is what? Secant squared xy squared times y squared times 1. So v prime is just y squared times secant squared xy squared. So let's collect what we have to find f sub x. Actually, g sub x. So this is what we have. And remember, u means partial with respect to x of u is u prime, and v prime is the partial with respect to x of v. But if that's the case, then the partial with respect to x of g of x is u prime v 2x times the tangent of xy squared plus uv prime plus x squared times y squared times secant squared of xy squared.